Hello. Today we'll discuss about diffraction of it. So let me just discuss what is the meaning of diffraction, and then we will go for the derivation related to the diffraction. So when light passes through the slit whose width, say d, is comparable or less than the wavelength of incident light, then what happens? It's spread out. Sometimes it's called the bending after passing through the slit. This phenomenon is called the diffraction. So the basic idea is you have a light source and you have a slit. If slit width is large, not comparable to the wavelength of light, then what we can get? The light will pass through this region and produce an illuminated area. And then after that we have the shadow region. So bright region and then the shadow region. But when d is comparable to lambda of same order, approximately same, then you will get a thing which is known as bending or spreading out. So what happens? At the center you will get a bright point, what was available in case of geometrical optics. Okay, the slit is very large. But then in the shadow region, which is supposed to be shadow region, there are also some bright fringes. So this is the case of the diffraction pattern. So you can see at the center region, this is very bright, but still there are some of the bright points available after its central mass. So this is the case of diffraction. So why diffraction occurs? So to explain the thing in a very simple way, one can consider when light waves are coming, so primary waves are coming. Now these primary waves are falling here around this slit. Now the number of secondary light sources, the electric fields which are available there. The number of secondary light sources is lesser in number in comparison to this geometrical optics case. Here also we get the wavefront, but the number of secondary light sources is quite large. So the individuality of the secondary light sources is almost absent over here. But in this case, when they are comparable, so individual light sources, secondary light sources play a very important role. So individually they are acting as a source of light. So now the individually waves are coming from this part, and when they are spreading out, they are going to overlap with each other. So in this case, the superposition of secondary light sources will produce diffraction pattern on the screen. In this case, the waves are not exactly superposing, they are producing effect. Directly they are producing effect over here. Now the secondary, when you have a production of secondary light sources, they are superposing and producing the effect. This is the case of diffraction. Sometime in a very simple way, people used to call the bending of light is known as a diffraction. So obviously one can think about this is the bright region, but here we can think about the shadow region. It is supposed to be shadow region. In this case also, somewhere here you can get a central maxima, and then you must have your shadow region. But it seems that they are bending like this. Rays are bending like this to produce some other bright points over here. So like this, some other bright points over here. Okay. Now, to explain diffraction or superposition of light, we are going to consider a simplest form of diffraction by a single source. And before going to this, let me just discuss about the types of diffraction. So there are two types of diffraction available. The first one is Fresnel diffraction. So what happens in case of Fresnel diffraction? The source and screen. The source and screen, they are at finite distance. Okay. So in this case, the wavefronts, what we are going to consider, they are spherical in nature. They have a sufficient curvature in the wavefronts. But the second one, the Fraunhofer diffraction, where source and the screen, the observable point, it's far enough. It is almost infinite distance. If this is infinite, then the wavefronts can be treated as a plane wavefront. So one can think about a very large sphere, and the part of this sphere is considered as a plane. Now, let me just discuss about the case of single slit diffraction. we're going to consider a Fraunhofer diffraction to simplify the experimental setup. So to start with this, we're going to refer a simple experimental setup diagram where we have light sources, the incoming wave. So sometimes we used to consider these are the primary waves. These are coming from a source and it is falling on the slit region. Now the slit is satisfying the condition. And what is this condition? The slit width, if this is d, this is comparable to the wavelength of the incident wave. They are of same order. If they are of same order, then the diffraction pattern will produce. So one can get a central maxima and so on. So what happens there? So the secondary waves, so just think about a wavefront somewhere here and then think about some of the secondary waves. They are allowed to pass through this. You have a space for them. But if you are considering the electric fields are point somewhere here, they cannot move in this direction. They have a obstacle in front. Now the few number of secondary light sources, when they are allowed to move in the forward direction, they will act as a source of light and they will produce light waves from this. And you can think about the second one, there will be second wave will be there. Then you can get the third one also, fourth one, and there will be few number of waves. The waves are moving in the forward direction and they will interact with each other. So when they are interacting, so we can use the concept of superposition, and by using this one can get the total intensity distribution pattern for the diffraction. So to do this experiment, to do this derivation for the single slit experiment, we are considering there are n number of secondary sources are available. And the gap between, so there will be n number 1, 2, 3, 4, 5, 6 up to n. And the gap between the secondary sources is given by delta. So if n is quite large, it's a mathematical expression. If n is quite large, then delta will be very small. It tends to 0. So they will be very close to each other. And the mathematical relation is n into delta. This is equal to d. What is d? D is the slit gap. So there will be n number of points with a gap of delta. So n into delta gives you the p. Now the waves are coming. So there are two possibilities. Just see here you can consider some of the rays which are moving in this direction, straight with the angle 0, and some of the rays which are in this. So you have a undeviated ray and the diffracted ray. So we can consider diffracted ray of different angles. So this may be θ1. Then you can consider another one with the angle θ2. So in this side you can also get θ1, θ2. So θ3, θ4 are also available. So obviously you can just see there will be a case of path difference except the central region. So in the central region what happens when rays are moving, they are covering a distance, the distance between the slit and the screen. But as it is for other points, the distance between the slit and the screen is a different distance. Now to explain this one, we are going to refer this particular picture. What is there? Here we are considering two light sources producing simple sinusoidal wave. So here we are considering 2-point crest and chart, 2-point red and blue. Now if the distance between these two sources is d, so when you are moving parallel, absolute parallel, the distance covered is equal. So the path difference, distance between these two is equal to 0. If path difference is 0, so obviously phase difference will also be equal to 0. Because we know the relation between phase difference and path difference is given as 2 pi. The phase difference is given as 2 pi by lambda into path difference. If path difference is 0, phase difference is also equal to 0. But consider the second case. In this case, what we are doing, the distance between the two sources is d, small d, no problem. But you have a screen here, somewhere here, and we are considering a point exactly at d by 2. So in between this d. So now here, Just look at this point. Now here, both the red points are touching each other. So here also the path difference is 0. So they are covering this distance and this distance, they are equal. So obviously the phase difference will also be equal to 0. So this is representing the central maxima position. But consider any other point. Now see, you have considered one particular point where the red and blue from two different waves, they are interacting with each other. So they are obviously in out of phase, or in other words you can say you have a path difference. So this one is covering some distance. Obviously the second one is covering a larger distance. So obviously there will be path difference, some value of path difference x or something. So you will get the corresponding phase difference. So in this case, in this particular picture, we have considered only 180 phase difference. So obviously one is at the top and another is the bottom. Obviously this, when they are interacting with each other, this will produce a dark patch. So how much is the path difference? So to calculate the path difference, what we are going to do, we are going to refer the slit, we are going to consider the undeviated ray, and we are going to consider the diffracted ray. And the angle between the deviated ray and diffracted ray or the deviated ray is represented by theta. Now just see the first one and the last one. What is the distance? If you draw a normal, so we can see this much is the additional distance covered by the last ray in comparison to the first ray. If you tilt your slit, if you just tilt this thing, tilt your slit, if your slit is somewhere here. Now from this point to this point, the distance covered is equal. So this is the angle. So from this particular point, this angle you can consider. So how much distance? This much is the distance, which is the additional distance covered by the last ray. If the angle between the undeviated ray and the diffracted ray or the deviated ray is angle theta, so this particular angle will also be theta. So you can have a triangle. So just I'm trying to draw the triangle over here. Simple. This angle is theta, this is known to us. Now what is this side? This side is D. What is D? This is the slit. Imaginary line we have to do. So what you have to calculate? We have to calculate what is the path difference this particular point. This distance. Okay. So one can simply say this is D. So if you are considering the first ray and if you are considering the last ray, the path difference will be D sin theta. Now if you are considering n number of secondary sources are there with a gap of delta, so then between 1 and 2, the first and second gap will be represented by delta sin theta, because this distance is delta. Now for the individual waves, this distance is delta. So obviously this will be represented by delta sin theta. Now this is clear. So now you know what is the path difference. So you can calculate what is the phase difference, 2 pi by lambda into delta sin theta. Now you have the phase difference. Okay. Now you will go for the superposition. Now what you have considered here, we have n number of secondary light sources and we have n number of waves which will superpose with each other. Now we are going to consider the wave equations. So the first wave equation was considered as A cos omega t. So one can consider sin omega t also with a phase difference of pi by 2. And the second one, then from there, so we can consider n number of secondary 1, 2, 3. So y1 we can consider. So what we have considered y1, this is as A cos omega. What is y2? The second one, this is considered as A cos omega t minus. Okay. Then we can also consider y3, we can consider y4 up to yn. And as we have considered the superposition of secondary light waves, so one can simply add all of them to get the superposed wave equation. Okay. So we're going to do these things to get the expression for this. Now come to this point. Now you have this. So this is the resultant field, or is to call the superposed field. So what is there? So this is A cos omega t, A cos omega t minus phi, A cos omega t minus 2 phi up to the nth value, up to yn. So this is represent yn, and this is yn. If you add all of them, your expression will be some constant, which is represented by E0 cos omega t minus half n minus 1 into phi. This is the time dependent, the phase part time dependent. But we are really interested about the amplitude part. As we are talking about light, we must think about the intensity factors. So what is E0? E0 is given as A sine n phi by 2 divided by phi by 2. So phi is the phase between the individual waves, individual secondary waves, and n is the number of secondary waves. Now just you think about sine phi by 2. So what is sine phi by 2? You can just consider sine theta. Okay, if theta is very small, then obviously sine theta is given as theta. Okay, so just you have considered sine phi by 2 as phi by 2. And to have a similarity between denominator and numerator, what we have done, we have multiplied with n. So this is given as n phi by 2. Okay, so sine n phi by 2 divided by n phi by 2 multiplied with n. Just you have just adjusted to n over. So now see, you have n into a sine n phi by 2. So what is n phi by 2? So phi you have already calculated. This is 2 pi by lambda into delta sine theta. And it must be multiplied with 2 divided by n. So this 2 and this 2 will be adjusted. So what is left? Left is pi into n into delta. So you have multiplication of n into delta. And what is n into delta? N into delta is the d, the slit. So pi d sine theta divided by lambda. So the resultant amplitude part is 0, or sometimes is to call A. This is given as n into a sine pi d sine theta by lambda divided by pi d sine theta divided by lambda. And as we have the similar expression, this is represented by beta over there. Now this is also beta. We have just given it by sine beta by beta. Now important question is, what is n into a? N is the number of secondary light sources and a is the amplitude of the individual waves. So this n into a is given as a maximum, or the central region, the effect of central region. Now this part, the sine beta by beta may vary from 1 to other values. So in this case, so this total amplitude value will vary. But when this is maximum, this factor, this is given by n into a. So just look at this resultant amplitude equation. This is equal to A is equal to n into a sine beta by beta, or n sometimes it's represented by a max. And what is beta? Beta is given as pi d sine theta divided by lambda. So one can just represent a is a function of beta. And mind it, remember it, the beta is function of theta. So we are basically thinking about theta. And what is theta? Theta is the angle between the undeviated ray and the deviated ray, or the diffracted ray. So effect of central maxima and for other maximas and minimas. So undeviated ray is the effect, also the effect of geometrical optics. But this deviated ray or the diffracted ray is the effect of physical optics, when the slit width is very, very small. Now this is the resultant amplitude part. Now the similar thing can also be proved by our simple diagram, which is known as the Phasor diagram. So the same consideration we have considered, but what we have considered that the individual waves. So we have considered n number of waves and we are adding all of them. So when you are adding, we have also considered they have a phase difference of phi. Okay. Just to consider, this is our first wave amplitude A, then we have the second one in this direction. So you can just consider this angle is phi. We can also consider you have some another angle, this is phi, this part is phi. So this is changing. So just for simplicity, consider we have n number of waves, okay, and they are having a phase difference of phi. If you keep on adding all of them, at a particular point in a very, very generalized form, the shape of the vectors will be given by this thing. So wave and its corresponding vector, when they are superposing, this is given by this particular curvature. Now we have a curvature where we have n number of a's. So the length of the curvature is given by n into a. And how to find the resultant thing? So obviously this particular color, this brown color one, is the resultant A. This is the resultant A. Now to do these things, what we are going to consider? We can just consider imaginary circle. Okay, imaginary circle one can consider. And its radius is given by r. Okay, and the angle, the total angle. Actually, we are talking about n into phi. N into phi is represented by delta. So if you are dividing into two parts, so the delta is given as delta by 2, and in this side is also delta. Now what you have to find? From this diagram, one need to find this particular length. This particular length. Now here this is a triangle. Just to think about a triangle. This side is known, this angle is known, and this particular side is known. One can easily write what is this particular side. So just name this one. This is x, this is y, say this particular point is z, and say this is b. So now at first we are considering a triangle which is x, p and z. This particular angle is delta by 2. This side is r. This is delta by 2. Okay. So now we need to find what is xz. Xz obviously given as r sine delta. So sine delta is equal to this by. Now what about xz? This is zy. So we have the same thing, r and delta over there. So this distance is also given by r sine delta by 2. So this is equal to z. What is the total length? Xz, which is basically a. In vector form, this is a. So a is given as r sine delta by 2 multiplied with 2. So this becomes 2r sine delta by 2r sine delta by 2. What is delta? Delta is equal to n into phi. Now again, what is n? N is the number of secondary light sources. And what is phi? Phi is the phase between the individual secondary rays. Now the second part is, we can use the simple geometry to get the idea about what should be the value of r. Now, if you are considering a circle, so this is the part of this circle, the arc length is given by n into a. Have n number of secondary light sources having length n, a. So the length of the arc length, this is equal to radius multiplied with angle. Which angle? This particular angle. So from this relation, one can write r is equal to n by delta. Okay, n by delta. Just to replace r is equal to na by delta. If you just replace it to n into a sine delta by 2. Now this is divided by delta. So what we are doing, we are making it whole divided. And this 2, I am taking it here. So this particular 2, I am taking it here. Now this is the expression where we have n into a sine delta by 2 divided by delta by 2. Divided by delta by 2. Now what is delta? Delta is equal to n phi. Delta is equal to n phi. So we have the expression. You have the similar expression. But we have a is equal to n into a sine beta by beta. So actually this n phi by 2 divided by n phi by 2 or something. So when you are here, you can easily get the expression for the beta. Now when you have this thing, you know you can calculate what is the intensity. because you know I, intensity, is proportional to amplitude square. When you are squaring this one, A max square. What is A max? N into A whole square. So I0 is represented by A max square, or this is equal to N. Secondary light sources into individual, and sine beta by beta square of this one. Now the most important part is what are the conditions where you will get the maximas and minima. Now you know they have some phase difference, they have some path difference and corresponding phase difference. But which phase difference values? You have your maxima and you have your minima. Now to do these things, so we have just taken 3 cases. Actually this should be 2, but to simplify our discussion, we have considered case 3. So for the case 0, this is the case of central maximum, when you have the delta is equal to 0. So mathematically we can say, when beta tends to 0, what is beta? Pi d sine theta divided by lambda. Beta tends to 0, sine beta by beta, this is equal to 1. Now the second case, if this is 1, if this is 1, so I is equal to I0. This is the case of central maximum. What is I0? N into A whole square, the central maximum. Now the second case, when beta is equal to 2m pi by 2 or m pi. Okay. So then what happens? Pi d sine theta divided by lambda m pi. Okay. So this is equal to d sine theta equal to m lambda. So theta value. So when theta value is sine inverse m lambda by 2, you will have the conditions for minima. What are the minima? Come to this point. So here you have bright point and then you have the dark point. These are the cases of minima. You have secondary cases. The central maxima. So I'm considering this is the case of central maxima. What we have? This is I0. N into A. Now the case of minima. Minima means this point. What is the condition? Minimum is beta must be equal to m pi. M means this can also be written as 2 m pi by 2. Okay. And the last case, obviously, if this is m pi by 2, so this will be the reverse case for the maxima. Which maxima? The secondary maxima. Okay. So in those cases, in these cases and in these cases, beta is given as 2m plus or minus 1 pi by 2. Okay, this is pi by 2. Now come to this point. Just see, you have your central maxima condition. Okay, then you have the condition for minima, and the condition for secondary maxima. Actually, these are case number 2 is the case of secondary maxima. And if this is plus, this is also applicable to minus. This is a periodic system. You can consider the left side and the right side. Now, the last portion for this single slit diffraction case is the position of maxima or minima. Graphically, how we can get the positions or the conditions for maxima and minima. Now, to do these things, we are going to take help of mathematics. So, in case of mathematics, if you have read about the idea about function, so one can plot a function fx. Okay, you can just consider y is equal to fx and this side this is x. So, you can have a function something like this. Okay, some function like this. Now, by simple calculus, by using simple calculus, one can find what are the conditions for maximas and what are the conditions for minima. So obviously somewhere here we will get a maxima. Okay, and somewhere here for those points we have the minima. So how to get this thing? So by using simple calculus, you need to differentiate this one, make it equal to 0, and then you will get the find the roots where you have the maxima and minima, the extreme values. And then we differentiate and you can get the conditions for maxima or minima. the same concept we are going to use to calculate this. What we are going to do? We are going to consider a function I is equal to I0 sine beta divided by beta whole square. I0 is obviously constant, number of secondary light sources, and the amplitude of the secondary light source is fixed, it's constant. So one can just think I, the intensity of the light on the screen, is as a function of beta. It's something like f as a function of x. Now what we can do? We can differentiate. One can differentiate I with respect to beta. di d beta, and if it is equal to 0, if di d beta intensity, if this is equal to 0, one can solve and find the roots for this extreme values. Then we can redifferentiate. We can go for second order derivative, put the values of the root. If this is greater than 0, so this is minima. If this is less than 0, this will be considered as maxima. So let me just check this thing. So we are going to differentiate this. So when you are differentiating, we get something like this. We have used the rule of multiplication. Actually, I have considered sine beta as a and 1 by beta as b. Okay. So we have this expression, something like this. A and b. So the first sine square beta taken as constant, and then 1 we are differentiating over 1 by beta square. And next case we have considered 1 by beta as constant, and we are differentiating over sine. This must be equal to 0. Now if you are rewriting this one can get, so you can just rearrange this one. This will be 2i sine beta divided by beta cube. This is equal to beta cos beta minus sine beta is equal to 0. So one can write the solution as sine beta is equal to 0. So it's in the form of x into y. This is equal to 0. So either x equal to 0 or y is equal to 0. So you need to check for both of them. So in one case sine beta is equal to 0, and obviously the another case will be beta cos beta minus sine beta. This should be equal to 0. And if you just rearrange this one, if you just divide both sides by cos, so this will be beta minus tan beta. This is equal to 0. Okay. Now when sine beta is equal to 0, we have already checked this thing. Sine beta is 0 means beta values are 2m pi by 2 or m pi s. Obviously, this is the position for maxima. If this is maxima, if this gives us the case of maxima, obviously this will give the case. If this is the case of minima, obviously this will give the case of maxima. Okay, this is the case of minima. If this is minima, this will give you. Now the question is, it's a very complicated one. Beta is equal to tan beta. This is equal to 0. Now when beta is tan beta, this is not a trivial problem. You really cannot solve beta is equal to tan beta. It's not really happening. Now to do these things, we're going to use a graphical method to solve this particular problem. So what we're going to do? We're going to use the concept as beta is equal to tan beta. So just we are assuming there are two type of curves. One is y is equal to beta, and the second one is y is equal to tan of beta. Okay, so there are two curves. Now when beta will be tan beta, when these two curves are intersecting with each other. When they are intersecting, so you will have the solution for beta is equal to tan beta. Now graphically how it looks like? It looks something like this. Just see, you have two curves. Y is equal to tan beta. You have an infinite nature. You all know tan having an infinite nature, not like our sine and cos. And you have the other one, y is equal to beta. Now the question is, what is y is equal to beta? Beta is not a constant, it's a variable one, remember this. So it's something like it is in the form of y is equal to x. So what will be the value of x? This will be the value of y. If this is 1, this is 1. If this is 0, this is 0. If this is 2, this is 2. You can have a positive value. You can also consider the negative values. Now, some of the points, they are intersecting. So, these are the points where you can get maximum. Just let me check it in the graphical form and just compare with those conditions. Let me just check it. Now, see, let me just take a red color one. Now, so the first one, the central maximum, obviously this is for 0. Okay, so we are not going for this particular one. Now, here we are considering m is equal to 0. M is some integer, m is equal to 1. Just consider the first one, m is equal to 1. So, we will have the condition for pi when m is equal to 1. So, when this is 1, at the point pi, you must get a minimum. Consider this particular point, this point. So, this particular point is okay. Then also we can check it for m is equal to 2. So, this is 4 divided by 2. Okay. Actually, this becomes 4 divided by 2. So, this becomes 2 pi. So, at 2 pi also we have the similar condition. Now, check it for the maxima. Which maxima? These are the secondary maxima. Where you will get this one? In the secondary maxima, you have a condition 2m plus or minus 1 pi by 2. I am considering m is equal to 1. Or first consider m is equal to 0. Make it simple. M is equal to 0. So, if m is equal to 0, it simply becomes pi by 2. So, what will be pi by 2? If this is pi, okay. So, somewhere here you will have pi by 2. Okay. So, pi by 2 you have the maximum. Okay. This is overlapping with central maxima. Consider the next one. Consider m is equal to 1. If m is equal to 1, so this will be 2 into 1 plus 1. So, this will become 3 pi by 2. Why do you have 3 pi by 2? This is pi, this is 2 pi. So, obviously pi plus 2 pi plus pi by 2. This gives you 3 pi by 2. So, where this will be pi and in between somewhere here you have 3 pi. Just take a different color, blue color I am taking. I'm taking this particular way. Okay. So, now see somewhere here. So, pi plus pi by 2, this gives our first secondary maximum. You can also check it for the second one. May consider m is equal to 2, m is equal to 3, and you have some of the maximum. Okay. So, a simple recapitulation. So, we have started with the idea of diffraction. What is the meaning of diffraction? Just consider two cases. Simple geometrical optics where slit gap is large, and in case of diffraction, slit gap is not so large. This is less and in comparison to wave. Then what happens? The secondary waves are forming. They are superposing and they will give some idea about spreading of light or bending of light where we should have a gated dark position. Okay. Still you will get some of the bright points. So, this is called the concept of bending over there, bending of light. It seems like. Now, we have mentioned about the types of diffraction, Fresnel and Fraunhofer. Now, the single slit diffraction was explained. Okay, we have explained the idea about the phase difference and corresponding path difference. Then we have considered the superposition of light waves, secondary light waves, n number of secondary light waves, and the resultant amplitude. And resultant amplitude, but it comes in the form of sine beta by beta, a function of sine beta by beta, where beta is given as pi d sine theta divided by lambda, where d is the slit width and theta is the angle of diffraction or angle of deviation. Now, by using the Phasor diagram, we can also solve the problem. You can come out at the same position of resultant amplitude, and from this resultant amplitude one can get what is the intensity. So, the conditions for central maxima, condition for minima and secondary maxima was also explained. Then comes the position of maxima and minima. So, to do those things, we have used a simple calculus and we have got the conditions for sine beta is equal to 0 for minima and beta is equal to tan beta. This is the condition for maxima. So, graphically, when y is equal to beta and y is equal to tan beta. They are intercepting. We get the position for maximum.